A battery of a given EMF is connected to a pair of parallel metal plates of surface area capital A, and the plates are separated by distance d. We have a beam of alpha particles that are accelerated through a potential difference V0. The alpha particles arrive at the plates, and when they enter the plates, of course, there will be some electric force acting on them. The question is, what must be the magnitude and direction of the magnetic field so that the alpha particles go through the plates without being deflected? So because of the potential difference between the parallel plates, there's going to be an electric force acting on the alpha particles. And we want the magnetic force to have the same magnitude and opposite direction, such that the alpha particles don't get deflected as they go through the region in between the parallel plates. Just a reminder, an alpha particle is made up of 2 protons and 2 neutrons, so its charge is equal to plus 2e, e being the elementary charge, and its mass is equal to 4 times proton's mass, m sub p. First, let's determine the direction of the required magnetic field. Now, if we look at the battery, the negative terminal is on top, so then this negative terminal will make the top plate negatively charged, and the bottom plate will be positively charged, the one that's connected to the positive terminal of the battery. Meaning the electric field between the plates will be pointing up from the positive plate towards the negative plate. So that's my electric field. And if you think about it, alpha particles is positively charged. As they enter the region in between the plates, there's going to be a force acting on them again towards the upper plate. So this is the electric force vector applied on the alpha particles. You can imagine a positively charged particle experiences a force in the same direction as the electric field, but also we know that the positive plate will be repelling the alpha particles and the negatively charged plate will be attracting them, so the electric force is pointing up. And we want the magnetic force to balance this out, so the magnetic force then should be pointing down like so. So this is F sub B, the magnetic force acting on the alpha particles, such that the alpha particles can go through the plates without being deflected. Now, if F sub B points down, what must be the direction of the magnetic field? Now remember, magnetic force is proportional to V cross B, and V being the velocity of the alpha particles. And B is the unknown vector, right? We don't know the magnetic field vector. So how can we get what direction of magnetic field will result in magnetic force pointing down, given that we have positively charged particles moving to the right? Now we're gonna do V cross B, B being unknown, and the result of V cross B is known. The result should be pointing down. So by the right hand rule, if you align your right hand in the direction of V, that's to the right, and whatever the direction of B is, your thumb should be pointing down. So align your right hand to the right in the following the direction of the velocity vector, and make sure your thumb is pointing down. In what direction can your fingers curl? Well, your fingers must be curling towards you or out of the page, like so. So this is the direction of the magnetic field. The magnetic field must be pointing out of the page, so that when we do V cross B, the result of following the right hand rule, the result is pointing down. Of course, the actual formula for F sub B is Q times V cross B. Q is a scalar, and in this problem it's a positive value, positive number. So the direction of V cross B directly gives us the direction of the magnetic force vector. Again, align your hand in the direction of the velocity vector, right hand, Curl your fingers in the direction of B out of the page, and your thumb will be pointing down. That's the direction of the magnetic force. Now let's calculate the magnitude of the magnetic field. As we explained earlier, we want the net force on the alpha particles to be equal to 0 so that they don't get deflected and they can continue along a straight path. So then we want net force in the vertical direction to be equal to 0. So this is Newton's first law that we're setting up here. And then in the next line, we open up the force equation. We have electric force pointing up, magnetic force pointing down. So then we want F sub E minus F sub B to be equal to 0. So those are the two forces acting on the alpha particles. And in the next line, I substitute the definition, defining formulas for each force. The electric force is equal to the charge of the particles times the electric field magnitude, and the magnetic field, the magnetic force is equal to charge times speed times the magnetic field magnitude times sine of the angle between the velocity vector and the magnetic field vector, which is equal to 90 degrees. So sine 90, this is equal to 1. And we set this equal to 0, so q's cancel, we can divide both terms by q. So as a result, we get E minus V times B equals 0. Now in the next step, we are going to determine expressions for the electric field E, because E is not given, and the speed of the alpha particles V, which is also not given. So what is it that's given in the problem? Let me actually circle what's given. The EMF is given, the plate area capital A is given, the plate separation D is given. These are also known, the charge and mass of the particles. These are known quantities. And finally, the potential difference across which the alpha particles are accelerating initially before entering the magnetic field region, before entering the region between the plates, is also given. So V0 is given, EMF is given, D, plate separation, plate area capital A, those are all given, in addition to the charge and mass of the particles. So next, let's come up with an expression for the electric field magnitude, capital E. Now let's remember, electric field is potential difference per unit distance. So the electric field in between the plates is equal to the voltage potential difference between the two plates divided by the plate separation D. And the potential difference between the plates is equal to the applied EMF voltage, because the plates are connected to this battery with EMF, and the plates are fully charged. So the potential difference between the plates is equal to the EMF of the battery. So then the electric field magnitude is equal to EMF divided by D, D being the distance, the plate separation between the two plates. Now let's find the speed of the alpha particles as they enter the region in between the parallel plates. Where does that speed come from? It comes from the fact that the particles are accelerated through this applied potential difference V0. Now, how does that work? Well, when you apply potential difference to some charged particles, initially they have electric potential energy and they're free to move, so that electric potential energy will turn into kinetic energy, and that's how the particles end up accelerating from rest. So the idea is that the potential energy, electric potential energy that the particles have at the beginning will turn into kinetic energy that they will have at the end, right before they enter the region in between the parallel plates. So here we're setting up that formula, that equation, electric potential energy equals kinetic energy. And electric potential energy is equal to the applied potential difference, the applied voltage V0, times the charge for a given particle. And it's going to be equal to the kinetic energy that the particle acquires at the end of this process, which is equal to 1/2 mv squared, m being the mass of a single alpha particle and v is the speed of a single alpha particle. Now the charge of each alpha particle is equal to 2e, 2 times e, the elementary charge. So 2 times e times v 0 is then equal to 1/2 times the mass, which is 4 times proton's mass, m sub p, times v squared. So that's what we have in the second line. The 2 on the left hand side and the 2 and 4 on the right hand side, they all cancel. We rearrange our equation to isolate the speed, lowercase v, which is equal to square root of e times v0 divided by m sub p. Now let's combine all this and go back to our previous equation, E minus V times V equal to 0. And then we are going to substitute the electric field magnitude, EMF divided by D, and the speed of alpha particles that we found here. Combine all that and isolate the unknown, capital B, the magnetic field magnitude. Here we have combined those two results in the original equation and rearranged our equation to solve for B. B is equal to EMF divided by D times square root of m sub P divided by E times V0. You may have noticed that there is one given quantity that we ended up not using. That's the plate area, capital A. It's rare, but it sometimes happens. Usually we do use all the given variables in a problem, but in this particular problem, plate area was not necessary.